Evolution is based on the idea of fitness, meaning the ability to survive and reproduce in a specific environment. It unfolds within an adaptive landscape similar to an optimization problem, where variation introduces diversity and selection gradually removes weaker solutions while favoring traits that enhance survival. Although evolution has no fixed objective, its outcomes often appear purposeful and well-directed. Organisms continuously anticipate changes in their surroundings, and successful prediction leads to reduced surprise and greater stability. Fitness is shaped not only by environmental conditions, but also by genetic relationships between traits and by interactions with other organisms, such as mimicry, which can provide temporary advantages in certain contexts. In dynamic and learning systems, objective functions become more complex and less predictable. Evolutionary algorithms capture this process by exploring solution spaces through variation and selection. Poor choices in representation or operator design can lead to premature convergence, limiting diversity and performance. This challenge often requires modifying representations, adjusting variation operators, or refining selection methods. The introduction of real-valued representations revealed that mutation can be more effective than crossover in many cases. To remain effective across different stages of search, evolutionary algorithms often rely on self-adaptation, allowing parameters and operators to evolve over time and improve exploration of the solution space. The human brain is composed of a vast, highly interconnected network of neurons that enable reading, breathing, movement, and thought. Each biological neuron has a level of complexity comparable to a microprocessor, making the brain a powerful nonlinear and parallel computing system. Through its ability to organize neurons structurally, the brain can perform certain computations far more efficiently than even the fastest digital computers. Neurons are highly connected elements, each linking to many others. A biological neuron consists of three main parts: dendrites, a cell body, and an axon. Dendrites form branching networks that receive electrical signals and carry them into the cell body. The cell body integrates these incoming signals and determines whether to activate. The axon then transmits the resulting signal to other neurons. Communication between neurons occurs at synapses, which are contact points between the axon of one neuron and the dendrite of another. The overall function of a neural network depends on both the arrangement of neurons and the strength of their synaptic connections, which are shaped by complex chemical processes. Research has shown that biological neural functions, including memory, are encoded in neurons and their connections. Learning occurs through the creation of new connections or the modification of existing ones. Although our understanding of biological neural networks remains limited, it is possible to construct simplified artificial neurons and train them to perform useful tasks. This idea forms the foundation of artificial neural networks, which are inspired by the brain's fundamentally different approach to computation compared to traditional digital computers. The history of neural networks has progressed in an uneven and complex manner. Early foundations were laid in the late 19th and early 20th centuries through interdisciplinary research by scientists from multiple fields. The modern view of neural networks emerged in the 1940s when Warren McCulloch and Walter Pitts demonstrated that artificial neurons could, in theory, compute any arithmetic or logical function. Their work is widely regarded as the starting point of the neural network field. Practical implementation began in the late 1950s with the development of the perceptron and its learning algorithm, which generated significant enthusiasm. However, it soon became clear that the basic perceptron could solve only a limited class of problems. In response, researchers introduced new learning methods for adaptable linear neural networks, some of which remain in use today. Interest in neural networks declined in the late 1960s due to limited computational power and a shortage of new ideas. This situation changed in the 1980s as advances in computing technology and the introduction of several key concepts revived the field. Two developments were especially influential. The use of statistical mechanics to explain the behavior of certain recurrent networks capable of associative memory, and the creation of the backpropagation algorithm, which enabled effective training of multilayer networks. Today, neural networks are widely applied and continue to evolve through both theoretical and practical innovation. Their strength lies in their parallel distributed structure and their ability to learn and generalize. However, they do not function effectively in isolation and must be integrated into a broader systems engineering framework, where complex problems are divided into simpler tasks and neural networks are applied where their capabilities are most effective. Artificial neural networks, commonly referred to as neural networks, are a technology with roots in many disciplines, including neurology, mathematics, statistics, physics, computer science, and engineering. They are designed as massively parallel distributed systems that mimic certain aspects of biological information processing. One of their most important properties is the ability to learn from data and to generalize, meaning they can produce appropriate outputs for inputs that were not encountered during training. Because of this learning and generalization capability, neural networks are applied to a wide range of problems such as modeling complex systems, time series analysis, pattern recognition, signal processing, and control applications. At the core of every neural network is the artificial neuron, which acts as the basic information processing unit. By combining many such neurons and organizing them into structured networks, neural systems are constructed that can solve complex and nonlinear tasks efficiently. This subsection focuses on the delta rule, a supervised learning method used to train single-layer perceptrons. The delta rule works by iteratively adjusting the weights and biases of the network to minimize the difference between predicted and actual outputs. Its principles can also be extended to multi-layer perceptrons, influencing training efficiency and the overall learning process. A critical factor in applying the delta rule is the learning rate, which determines the size of weight updates. The choice of learning rate directly affects the speed of convergence and the stability of learning, with rates that are too high causing instability and rates that are too low slowing progress. The delta rule has been applied in various real-world domains, including image recognition and natural language processing, where it helps networks learn patterns and relationships from complex datasets. When compared with other learning algorithms, such as gradient descent and backpropagation, the delta rule offers a simpler approach for single-layer networks, but may be less effective for deeper, multi-layer architectures. Common challenges in using the delta rule include overfitting, where the network becomes too closely tuned to training data, and underfitting, where it fails to capture underlying patterns. Addressing these challenges often involves techniques such as regularization, proper selection of learning rates, and careful design of network architecture to balance learning and generalization. This subsection covers several important aspects of neural network training and learning algorithms. It begins with the criteria that ensure the perceptron training algorithm converges, meaning it will ultimately find a set of weights capable of correctly classifying the input data. Understanding these criteria is essential for guaranteeing reliable learning in single-layer networks. The discussion also addresses overfitting and underfitting, explaining their causes and symptoms. Overfitting occurs when a model learns the training data too closely, capturing noise rather than general patterns, while underfitting happens when a model fails to capture the underlying structure of the data. Strategies to mitigate these issues are crucial for building robust models. Gradient descent is described as a foundational optimization method, highlighting its advantages over the delta rule, particularly in handling multilayer networks. Building on this, the backpropagation algorithm is introduced, emphasizing its central role in efficiently training neural networks by propagating errors backward to adjust weights. Alternative learning algorithms are also discussed, including support vector machines and decision trees, which address certain limitations of the delta rule and offer complementary approaches to classification and regression problems. Finally, real-world examples illustrate how image recognition systems successfully overcome challenges related to overfitting and underfitting, demonstrating the practical effectiveness of these learning strategies. The overview covers core concepts in machine learning and image recognition, including the implementation of a single-layer perceptron and its training algorithm, highlighting its ability to learn from labeled examples. The delta rule is explained as a method for updating network weights to minimize error. Support vector machines are compared with neural networks for image recognition, outlining their strengths and weaknesses. Real-world challenges, such as variations in lighting, occlusion, and image quality, are discussed for their impact on recognition accuracy. The history and evolution of perceptrons are traced, showing how modern neural networks have addressed their limitations. Finally, hybrid models combining neural networks with other learning algorithms are introduced, illustrating how these approaches can enhance performance in specialized applications. Backpropagation is a core technique for training multilayer neural networks, allowing these models to learn complex functions through systematic weight adjustments. This method is underpinned by the universal approximation theorem, which states that a feed-forward neural network with at least one hidden layer can approximate any continuous function, provided it has a sufficient number of neurons and properly configured weights. The backpropagation algorithm utilizes gradient descent to minimize error by propagating the loss backward through the network, iteratively refining the model's parameters, and enabling the network to achieve progressively higher prediction accuracy. In addition to backpropagation, cross-validation is essential for assessing the performance and generalization capability of neural networks. By dividing the dataset into training and validation subsets, researchers can ensure that the model performs well on unseen data rather than simply memorizing the training examples. The discussion also explores radial basis function (RBF) networks and their associated training algorithms, highlighting an alternative approach to function approximation. RBF networks employ radial basis functions as activation functions, offering benefits such as faster convergence and effective handling of nonlinear relationships. Examining RBF networks provides valuable insights into their unique strengths, contributing to a broader understanding of neural network architectures and their practical applications across diverse domains. Uncertainty and vagueness play a critical role in a wide range of real-world applications, particularly in systems where data is incomplete, ambiguous, or imprecise. To address these challenges, the introduction of fuzzy membership functions is essential. Unlike traditional set theory, which relies on strict binary classification, fuzzy membership functions allow elements to belong to multiple sets simultaneously, each with a specific degree of membership. This approach provides a flexible framework for modeling and reasoning about complex systems, enabling a more nuanced and realistic representation of data and relationships. By incorporating degrees of membership, fuzzy logic facilitates the handling of ambiguity and partial truth, which is especially valuable in areas such as decision-making, control systems, pattern recognition, and expert systems, where human reasoning often involves imprecision and subjective judgment. The use of fuzzy membership functions allows computational models to mimic human-like reasoning, improve interpretability, and make more informed decisions under conditions of uncertainty. Moreover, this approach enhances the ability to model nonlinear relationships and dynamic behaviors in complex systems, providing a robust and adaptable methodology for tackling problems that traditional binary logic cannot adequately address. Fuzzy logic provides a powerful framework for reasoning and decision-making when dealing with imprecise, ambiguous, or incomplete information, thereby enhancing the quality and reliability of decisions in complex systems. By allowing elements to belong to multiple sets with varying degrees of membership, fuzzy logic enables a more nuanced representation of uncertainty than traditional binary logic. This flexibility is particularly valuable in modeling real-world phenomena, where data is often noisy, partial, or subject to interpretation, and where human reasoning frequently involves ambiguity and subjective judgment. Building on these principles, fuzzy clustering algorithms such as fuzzy C-means and possibilistic C-means extend the concept of membership to the grouping of data points in unsupervised learning tasks. Unlike traditional clustering methods, which assign each data point to a single cluster, fuzzy clustering allows each point to belong to multiple clusters simultaneously, with varying degrees of membership, reflecting the inherent ambiguity in many real-world data sets. These algorithms are widely applied in areas such as pattern recognition, image segmentation, and data mining, where they improve the classification of data sets with overlapping or unclear boundaries and enhance the interpretability of results. In addition to clustering, fuzzy classifiers, including fuzzy k-nearest neighbors, provide robust methods for supervised learning in environments characterized by uncertainty. By incorporating degrees of membership into the classification process, these models can better handle noise, outliers, and ambiguous instances, resulting in higher accuracy and more reliable predictions across complex data sets. Such approaches are particularly useful in applications like medical diagnosis, financial modeling, and environmental monitoring, where the input data is rarely precise or complete. Furthermore, fuzzy measures and fuzzy integrals offer systematic tools for quantifying uncertainty and integrating fuzzy information into coherent decision-making models. Fuzzy measures generalize traditional probability measures by allowing the assignment of importance or weight to different subsets of data, while fuzzy integrals provide mechanisms for aggregating these weighted values to make informed decisions. This combination enables decision makers and computational models to synthesize imprecise information, evaluate trade-offs, and prioritize actions in a principled manner, even when faced with complex and conflicting data. Overall, the study and application of fuzzy logic, from membership functions to clustering algorithms, classifiers, and fuzzy measures, provide a comprehensive toolkit for handling uncertainty in a variety of domains. These methods not only enhance decision-making processes, but also improve the interpretability, flexibility, and adaptability of computational models, making them invaluable in areas ranging from artificial intelligence and machine learning to control systems, expert systems, and real-world data analysis. By embracing the inherent fuzziness of real-world information, fuzzy logic enables systems to operate more intelligently and robustly, bridging the gap between human reasoning and computational modeling. Fuzzy logic provides a robust and flexible framework for reasoning, modeling, and decision-making in environments characterized by uncertainty, vagueness, and incomplete information. Unlike classical binary logic, which strictly categorizes elements as either belonging or not belonging to a set, fuzzy logic introduces the concept of degrees of membership, allowing elements to partially belong to multiple sets simultaneously. This capability is essential for accurately representing real-world phenomena, where data is often noisy, ambiguous, or subject to human interpretation. By capturing the nuances of imprecision, fuzzy logic enables computational models to emulate human-like reasoning and make more informed adaptive decisions. A central component of fuzzy systems is the fuzzy membership function, which quantifies the degree to which an element belongs to a particular set. These functions allow for a smooth transition between full membership and non-membership, facilitating the modeling of gradual changes and ambiguous boundaries in data sets. For example, temperature, risk assessment, or customer satisfaction are rarely absolute values. Fuzzy membership functions provide a natural way to encode such continuous variables in computational models. Building on these foundations, fuzzy clustering algorithms such as fuzzy C-means and possibilistic C-means extend the flexibility of fuzzy logic to unsupervised learning tasks. Unlike traditional clustering methods, which assign each data point to a single cluster, fuzzy clustering allows points to belong to multiple clusters with varying degrees of membership. This approach is especially valuable in domains such as image segmentation, pattern recognition, and bioinformatics, where data often overlaps or exhibits complex relationships that cannot be captured by hard clustering. Fuzzy clustering algorithms improve the interpretability and robustness of results, helping analysts identify meaningful patterns in ambiguous data sets. Evolutionary computation is a powerful area of artificial intelligence inspired by the principles of natural selection and genetics. By simulating evolutionary processes such as selection, crossover, and mutation, these algorithms are able to efficiently explore vast solution spaces and discover optimal or near-optimal solutions. Their adaptive nature allows them to perform exceptionally well in dynamic and complex environments where traditional optimization methods often struggle. This video explores both the theoretical foundations and real-world applications of evolutionary computation. These techniques are widely used in engineering design, artificial intelligence, financial modeling, and bioinformatics, where they provide innovative and flexible solutions to challenging problems. Their ability to adapt over time makes them an essential tool in today's rapidly evolving technological landscape. The discussion also highlights the role of evolutionary algorithms in learning tasks such as regression, clustering, and control systems. In regression problems, evolutionary methods can effectively identify optimal parameters and uncover hidden patterns in data. In clustering, they dynamically adapt group structures to improve data interpretation and decision-making. When applied to control systems, these algorithms continuously learn from their environment, enabling robust and efficient performance in fields like robotics and automation. In addition, the video introduces the concept of collective intelligence and its influence on evolutionary computation. Algorithms such as particle swarm optimization, differential evolution, and ant colony optimization are examined, showing how cooperation and shared experience among agents can lead to faster convergence and better solutions. By drawing inspiration from natural collective behaviors, these methods demonstrate how evolutionary learning continues to push the boundaries of optimization and intelligent problem solving across diverse domains. Evolutionary optimization techniques have gained significant traction in the field of artificial intelligence, particularly for enhancing the performance and adaptability of neural networks. By evolving both the connection weights and the network topology, researchers can develop models that are more efficient and capable of learning highly complex patterns without relying solely on gradient-based training methods. A well-known example of this approach is the cart-pole system, where a fully connected, recurrent neural network is evolved to control a dynamic and unstable environment. Through evolutionary algorithms, the network parameters are optimized in real time, enabling the system to maintain balance and stability even when managing multiple poles. This demonstrates the strength of evolutionary methods in solving control problems that involve continuous adaptation and nonlinear dynamics. Beyond control systems, evolutionary optimization also plays a vital role in classification tasks, such as breast cancer detection. In this context, a feed-forward neural network is trained to analyze medical data and identify patterns associated with cancerous cells. By evolving the network's architecture and weights, evolutionary algorithms significantly enhance classification accuracy and robustness. This leads to more reliable diagnostic systems, supporting earlier detection and improved patient outcomes. Overall, the versatility of evolutionary optimization highlights its importance in advancing neural network applications across a wide range of domains, from robotics and autonomous systems to healthcare and medical decision support. The semi-trailer truck backer upper problem is a classic and powerful case study for applying evolutionary algorithms to real-world control challenges. Due to the articulated structure of the truck, controlling its motion, especially while reversing, presents significant complexity. The trailer's ability to swivel independently behind the tractor creates highly nonlinear dynamics, requiring the control system to continuously manage the interaction between both components. Traditional control methods often struggle with such complexity, particularly in tight spaces where precision and adaptability are critical. Evolutionary algorithms offer an effective alternative by evolving control strategies through simulation, evaluation, and adaptation. By iteratively optimizing candidate solutions, these algorithms can discover robust maneuvering behaviors without requiring an explicit mathematical model of the system. This makes the truck backer upper problem an ideal benchmark for evolutionary approaches, demonstrating their ability to handle dynamic, uncertain environments and complex control tasks. The success of these methods highlights their broader potential in autonomous vehicle control and other real-world robotic systems. Games can be viewed as a miniature reflection of life itself, encapsulating the complex dynamics of strategy, decision-making, and goal pursuit. Every game operates under a distinct set of rules that shape player interactions and define the structure within which decisions are made. As players engage with a game, they continuously interpret inputs from their environment, weigh possible actions, and align their choices with desired outcomes. This process appears across a wide range of contexts, from competitive environments such as poker to cooperative settings like team sports, where collective effort is essential to achieving shared goals. Beyond entertainment, games mirror the broader patterns of human existence. In everyday life, individuals frequently navigate the balance between personal ambitions and collective responsibilities, much like members of a soccer team working together toward a common objective. In such situations, success extends beyond individual achievement and depends heavily on effective collaboration. This interplay between competition and cooperation highlights the complexity of human behavior and underscores the importance of strategic thinking, adaptability, and social interaction in both games and real life. Life often reflects the same intricate dynamics found in games, where achievement is not solely defined by winning or losing, but by the ability to manage relationships and align collective aspirations. This is particularly evident in contexts such as marriage and parenting, where teamwork, compromise, and mutual support can lead to fulfillment regardless of specific outcomes. In these scenarios, individual goals may differ, revealing the nuanced and evolving nature of human relationships. Much like courtship, where one individual may seek closeness while the other remains distant, life presents continuous moments where cooperation outweighs direct competition. Game theory provides a powerful framework for understanding these interactions. It extends beyond traditional competitive games by offering insights into how individuals and groups plan, negotiate, and allocate resources to achieve their objectives. Evolutionary algorithms further enrich this perspective by modeling decision-making processes that adapt over time in response to the actions of others. This iterative evolution of strategies mirrors natural systems, where survival and success depend on continuous adaptation within dynamic environments. Concepts such as the iterated prisoner's dilemma illustrate these principles, emphasizing the critical role of adaptability, foresight, and strategic reasoning in both evolutionary computation and the complexities of everyday life. Differential evolution is a population-based optimization algorithm designed to search for optimal solutions in real-valued spaces. It was introduced by Storn and Price in the mid-1990s and emerged around the same period as particle swarm optimization. The method is particularly effective for solving complex optimization problems, where the goal is to find the maximum or minimum of a function. The algorithm works with a population of candidate solutions where each individual represents a possible answer to the problem. The population is usually initialized randomly, although prior knowledge about the search space can also be used to guide the initial setup. Differential evolution operates through three main mechanisms: mutation, recombination, and selection. Its most distinctive feature is the mutation process, which relies on the differences between individuals in the population. Instead of using random changes, new candidate solutions are generated by using the vector differences between selected individuals. This allows the algorithm to adaptively explore the search space based on population diversity. To perform mutation effectively, the population size must be at least 4 individuals, because each mutation step depends on 3 distinct individuals selected at random. These individuals influence the movement of another individual and guide the search toward better solutions. After mutation and recombination, a selection process is applied to compare the newly generated solution with the original one. The better performing solution is kept for the next generation. Through repeated iterations, this process enables the population to gradually converge toward an optimal or near optimal solution. Ant colony optimization, ACO, is a powerful computational approach inspired by the natural behavior of ants as they search for food. As ants move through their environment, they deposit pheromones that act as a communication mechanism within the colony. These pheromone trails guide other ants toward food sources and help the colony collectively discover the shortest and most efficient paths. Trails that are used more frequently become reinforced with stronger pheromone signals, creating a positive feedback loop vacuum that attracts even more ants. Through this balance of exploration and exploitation, ant colonies are able to adapt quickly to changing environments and efficiently locate resources. When applied to the traveling salesperson problem, ACO provides an effective framework for modeling how ants explore a set of cities. Each ant begins from an initial city and travels through the remaining cities while depositing pheromones along its path. As ants complete their tours, the pheromone levels on the traveled routes are updated, strengthening shorter and more efficient paths while reducing the influence of longer ones. Over multiple iterations, this collective learning process enables the colony to converge toward optimal or near optimal solutions. With a population of 50 ants working together, the algorithm demonstrates how cooperation and adaptation can lead to effective problem solving while minimizing overall travel distance. The study of evolvable hardware introduces exciting opportunities for applying evolutionary principles to physical systems. By incorporating concepts from evolutionary algorithms into hardware design, engineers can take advantage of the adaptability inherent in physical structures. Techniques such as using random number generation to modify device configurations, including systems based on hinged plates, illustrate a practical approach to optimization. This iterative process of variation and selection closely resembles biological evolution, allowing efficient designs to emerge through gradual improvements. Experimental methods such as wind tunnel testing further enable researchers to refine hardware configurations to achieve desired outcomes, including reduced aerodynamic drag. This approach highlights the importance of adaptability and interaction among system components. In a manner similar to how ant colonies collectively discover optimal paths, evolvable hardware systems improve through random changes and selective reinforcement. This fusion of biological inspiration and engineering practice demonstrates how interdisciplinary approaches can drive significant technological innovation. As the field of data analytics continues to evolve, organizations are increasingly recognizing the transformative impact of integrating advanced technologies into their strategic frameworks. Predictive analytics plays a vital role in enhancing the accuracy of market forecasts while enabling businesses to identify emerging trends and shifts in consumer preferences more effectively. By applying sophisticated algorithms, companies can analyze large volumes of data to extract actionable insights that guide marketing decisions. This proactive approach allows organizations to anticipate changes in consumer behavior and respond quickly, helping them maintain a competitive advantage in an increasingly dynamic marketplace. Despite these advantages, the use of extensive data sets must be carefully balanced with ethical considerations related to privacy and data security. As organizations collect and analyze consumer information, they must navigate complex regulations that govern responsible data usage. Ensuring regulatory compliance while maximizing the value of data analytics is essential for maintaining consumer trust. Additionally, excessive reliance on predictive models can result in simplified assumptions about diverse market segments. A deeper and more nuanced understanding of consumer behavior is necessary to protect niche markets and encourage innovation in marketing strategies, ultimately strengthening relationships between businesses and their audiences. Although advanced technologies provide valuable support for decision-making, they can also create a false sense of certainty. This perception may cause organizations to underestimate the complexity of human behavior, which is often unpredictable and difficult to quantify. An overemphasis on personalization can overwhelm consumers or make them feel pressured by targeted marketing efforts. In such cases, privacy concerns and consumer fatigue may arise, potentially weakening brand trust and long-term loyalty. Conversely, a thoughtful and transparent approach to data usage can generate meaningful insights into consumer needs and expectations. When organizations prioritize genuine understanding rather than relying solely on data metrics, they are better positioned to build authentic and lasting connections with their audiences. Businesses must carefully balance personalization with ethical data practices to remain inclusive and credible in their messaging. By embracing diverse perspectives and experiences, organizations can enhance their marketing strategies while avoiding the creation of narrow echo chambers. This openness fosters stronger engagement, supports innovation, and contributes to sustainable growth.